Hey everyone, and welcome. Today we are diving into something truly special, one of nature's most bizarre and, let's be honest, seemingly impossible tricks, a wave that basically travels forever, a perfect little pulse of energy that just refuses to die down.
I mean, really think about that for a second. You toss a pebble into a pond, you see those ripples spread out, right? They get weaker and weaker, and then they're gone. Or picture a surfer on a perfect wave. It's got that beautiful shape, but eventually it always crashes onto the shore and disappears. But what if it didn't? What if that ripple just kept on going, holding its perfect shape for miles and miles?
And that's the whole mystery right there. On one side, you've got every wave you've ever seen. Its energy spreads out, it dissipates, it just vanishes. But on the other side, you've got this strange thing, this soliton. It holds its shape perfectly, travels at a totally constant speed, and seems to just ignore all the rules. So how on earth is that possible? Well, to get to the bottom of it, our story doesn't start in some high-tech lab. Nope. It starts on a path next to a canal, way back in the 19th century. This is the beginning of a really great scientific detective story.
Okay, so picture this. The year is 1834. A Scottish engineer named John Scott Russell is watching a barge get pulled down a canal. All of a sudden, the barge just stops. But a single, perfectly smooth wave breaks off from the front and just keeps going. And it doesn't fade, it just keeps rolling along. Russell was so captivated, he literally jumped on his horse and chased it for more than a mile before he finally lost it. He had just seen something that no one had ever properly written down or studied before.
So Russell saw this thing, but he couldn't explain it. It would actually take decades for science to figure out the beautiful secret behind this crazy, unchanging wave. So let's get into the physics of it.
All right, the first ingredient you need is a force called nonlinearity. Now, put simply, this is just the tendency for the top of a wave to move a little faster than the bottom. It causes the wave to lean forward, get steeper, and eventually, topple over and break, just like an ocean wave hitting the beach. Think of it as a force that wants to bunch everything up.
And the second ingredient is a force that does the exact opposite. It's called dispersion. And this is what we see with that ripple in the pond. It's the natural tendency for a wave's energy to spread out, which makes the wave get flatter and wider until it disappears. So this is a force that wants to spread everything out. So here it is, the big reveal. What happens when these two totally opposite forces, the steepening effect and the flattening effect, are in a perfect, delicate balance with each other? Well, you get a soliton. The force pushing the wave up is perfectly canceled out by the force spreading it out. The result? A single, unbelievably stable wave that just cruises along forever. And this isn't just some lucky fluke of nature. It's all laid out perfectly in some really elegant math, most famously in what's called the KdV equation. The math shows exactly how these two forces can lock together to create this incredible thing. It's just a stunning example of how math is kind of the hidden language of the world around us. Now, I know this might all sound like a cool but kind of obscure thing that happened in an old canal, but it turns out the discovery of solitons has had a huge, and I mean huge, impact on our world today, in ways you probably don't even realize. So get this, solitons are pretty much the reason we can send pulses of light, which is our data, through fiber optic cables across entire oceans without the signal turning to mush. They're also critical for modeling tsunamis, which are basically a kind of giant, scary soliton. And it doesn't stop there. The idea is used in plasma physics and even in biology, where these models help us understand how DNA works. It's everywhere.
As amazing as all that is, we've saved the weirdest, most mind-bending property for last. It's a behavior that really makes solitons something special, totally unlike any other wave out there.
Okay, so if two normal waves crash into each other, you just get a chaotic mess, right? A splash. But not solitons. No way. When two solitons are heading toward each other, they pass right through one another. And when they come out the other side, they have the exact same shape and the exact same speed as they did before. It's like they remember who they are. This behavior is it's wild. They interact like solid objects, like little particles bumping into each other. But they're not solid at all. They're just pure energy. They're waves. And this strange dual personality is why scientists are still so fascinated by them. So yeah, from a random discovery made on horseback all the way to becoming the backbone of our global internet, the soliton is just this perfect example of a hidden rule of nature.
one that was found by pure curiosity and explained by the beautiful language of math. It's really a powerful reminder that the world is filled with these incredibly elegant and surprising things. So next time you see a ripple in a puddle, give a little nod to its amazing cousin, the wave that literally never dies. And that kind of leaves you with one last big thought, doesn't it? If a phenomenon as perfect and as strange as the Soliton was just hiding out in a simple canal, what other beautiful pieces of math are all around us, just hiding in plain sight, waiting for someone to notice?